Hi everyone, Martin here. Welcome to the In the Loop. I wanted to update you on the Sensing Joy project. This is part 3. The thing has actually taken some photographs, or well, certainly created some images. So I just wanted to share little videos of those being created and the pictures that it's made. Here's the first one. This actually takes quite a long time to do. It's probably 3 or 4 minutes worth of sort of stirring the joystick around. You can see it's kind of slowly building up. And does it look like that? I'm not sure. Okay, here's another one. This one I think was the side of my face. So I think you can see that there's maybe a head there. This one was just looking at a light, I think, just pointing the joystick at the light and swirling around and swirling around, and that's what you get. See that one building up. You're never going to guess what this one is. Goes. This is actually the garden. I think it's quite... You can see the areas of light and dark anyway. This one here is interesting because I added a form of auto exposure, so as this goes on you can see the brightness changes again, and also the pixel size is bigger. But this is a picture of my face, I think, or a sort of scan of my face. Here's another picture, again face again. This was another one of the light. This one's interesting because of the dots. I found out that that's the garden again. Another one, scan of the light with a larger pixel size. You're never going to guess what that was. It's the laundry. Okay, this one, just the light, I think. I think this is my favourite one. There you go, it's actually a scan of my face, actually looking down at the joystick, and then I think there was a light behind me. Here's another kind of abstract. And here's the original. Here's the original construction, and what I did is I moved the Raspberry Pi actually into the box, so it became one box instead of two. So here is the final thing. Just joystick, and the Raspberry Pi and everything is inside, and power supply. I do need to show you something extremely cool that I discovered with this, and I'll just demonstrate that to you now. So this has really been a project, a voyage of discovery, this project, finding all sorts of things along the way. Like, I don't know, adding auto exposure, and in a minute we're going to talk about averaging and trying to work out about averaging, but this was really cool. I found for my phone, an XWindows server. So that allows me to actually monitor what the Raspberry Pi is doing on my phone, which is great, which meant I could take the Pi and my phone outside, and then I can see what's going on. I'll demonstrate that for you now. So if I run up the application on the computer here, and then start moving the joystick around, hopefully you can see that the actual image is growing on my phone, which makes this whole thing completely mobile. I'm definitely going to be using this X server a lot more in the future. So it's clear from the playing with the physical box that it's going to take quite a long time to actually generate an image, and also the images that I've been creating are quite difficult to manage, because I don't know if they're in focus, I don't know if they're properly exposed, I don't know how much errors there actually are in the XY position of the joystick. I don't know how much noise there is. You can see from the pictures that they're not very easy to interpret, and also they're square, and the camera kind of has I guess scans kind of across the square. So also I don't know whether their pictures are actually quite fisheye in terms of what they're delivering. So before I kind of stopped with the project and gave up, I thought one final thing I could do is actually try and simulate what's going on, and see if by simulating it I could gain any additional insights into the process. So what I did is I took this picture here, or take any picture, take a picture, and I thought what I'll do is I'll pixelize it, and then see if from like averaging it I can actually recreate the picture. So is it possible with this pixel camera that I've got to actually create the picture anyway? You know, is there actually a picture able to be created if it's been averaged? So let's have a look at that here. I've cut it down to 800 by 800, which is the size of screen that I was using with my 1 pixel camera. Although the 1 pixel camera has got quite a huge definition, it can actually do 0 to 32768 in terms of A to D conversion, so it can actually create a huge resolution, although I don't know how much of that would be noise. Right, so the first thing I did with this picture is in software is let's turn it into pixels. Let's do it 20 by 20 and also make it monochrome. So this is what you get. You get sort of a rendering of the picture like that. So that's the original. That's the. But what you saw there was lots and lots of renderings of the picture. The reason being that my granularity of being able to actually point the sensor at the world is very granular. It is very fine, but the resulting data that it sends back is obviously averaged over quite a large area. So if I was to point the camera, the single pixel camera, pixel by pixel, knowing exactly how big they are across a scene, it should look like that. But when you saw it running there, I can move the camera much more slowly than I can the pixel size. So with this simulation, here is only one version of the image, and when you saw it scrolling there, I'll scroll it again. Here's the original. This is 20 by 20. It can make 400 different pictures. You can watch these 400 go by. They're all very similar, but each is unique. So what occurred to me was, if I take those 400 pictures and average them all together, what would I actually get? So let's look at that. So here we go again. Here's the original picture. And what I'm going to do is average those pixelated pictures, average all 400 of them together, and you'll see as we go on, more and more pictures get added to the average. And as more pictures get added to the average, so this is a view of the original scene. I haven't cheated in any way. I've averaged it down to 20 by 20 pixels, and then I've just averaged all of those 400 pictures back together again, and this is what you get. So it looks to me like it is possible to drag back a fairly representative version of the original scene. I'll do it again, but let's do it with 100 pixels this time. Well, with 100 by 100 pixel, it doesn't really look like the original anymore. Okay, so let's go back to our 20 pixel example. Do that process again. Now, the process is quite tedious and quite time consuming, and you can see the bigger the picture gets, the harder it becomes. So, is there another way of doing this? Well, what I tried next is the simplest thing, which is just to take the value from each point that I can scan and just plot them. So, where there's a 20 by 20 pixel square, the top left hand corner first point is the average value, and then move across and move across and move across. And when you do that, you actually end up with almost exactly the same photograph. So just taking the average values and plotting them one after another, looks like it builds up, which is fairly intuitive in terms of what you'd expect, builds up a reasonably good photograph. The next thing I thought I'll have to describe on paper was to try and recapture some of the values. I was wondering if I could actually generate some more information out of the picture by trying to guess what the edges might be. I'll draw a picture of demonstration of the maths for that, or the thinking for that, in a minute. I've got my favourite thick pens, so let's have a go. Here's the world again. This is the world. Here's a measurement of the world. If I move my measurement across by 1 pixel, so I've got two values here, V1 and V2. Two values here. If I subtract V2, so if I take V1 and take away V2, what am I left with? I'm actually left with the value of that, which is fantastic, because now my sensor has vastly increased in terms of its sensitivity. There is only a slight fly in the ointment, which is I've also got minus this pink bit. So although I've improved the sensitivity of my camera, I've got this bit here. So let's pretend that bit doesn't exist. Let's pretend that doesn't exist. Now my camera's gone from whatever that resolution was down to 1 pixel. And this is the kind of algorithm that I've used to make the both X and, if you look at the Y version of this. So there's the first scan, and then the next pixel is down here. Again, now my green area, I've actually now got a value for those pixels. So this is like a vast improvement, but whoops, I'm going to forget about the pink bit. So you can see those two pictures, and you can see that they have a lot more kind of well, they look sharper, but actually they don't actually give you any more information, because this is still an unknown. So let's look at that. So here I've applied the algorithm going left to right, and you can see it's kind of sharpened up the image left to right, so we now have a kind of spiky, sort of more edgy looking picture. And if we do it top to bottom, again we have a more edgy looking picture. This hasn't actually added any more information into the picture. All it's actually done is just make it look like it's less averaged. The next thing I thought of was, what if the when I've created that first image from the averaged values, what if I then average that again? So look at that image and say, oh, I know what the average value should be, so average the values on the new image. I know what the average value should be, and then revisit that and see what is the average value of that pixel actually now, and then correct it for the missing. Again, I'll have to describe that below. Here's our world again. Since this is the inner loop and it's about algorithms, I thought there must be a way to iterate this. So there must be some iterative process that we could use to iterate this. So here's our value. So now I'm going to bring my 800 by 800 screen in here. So that's that value there. Then we move. So now what I'm doing is just moving across one pixel at a time. Just move across. Here's the blue value, so that's that value there. And then we move across another pixel. It's the pink value. So this is how the original picture was kind of grown and built up. Let's keep going across. There's a blue one. And you'll see in the picture that I created that the edges are actually missing, because all of this area here isn't. It's at the first point that becomes available to me is actually in the middle of the green square. Right, so now maybe you might be able to see where this is going. As these pixels build up across and start building me up this is now going to start building me up an image. Like this. But there's one thing I do know. There's one additional piece of information that I've got here that I can use, which is the green value here in the real world. I know what that is. I know what the average value is. So if I take the same pixels on my newly created image, like that, take those pixels, I already know that value. I know what the real value is for that pixel. And funnily enough, if I average all these together, they should give me the value that I got from the sensor from here. So I've got an opportunity to iterate here, because these values don't add up exactly right to the value that I saw from here. So from this black square here, so in this square here, that would be the value that I should be getting from those pixels. But I know that they don't match up. Because of all the averaging that's gone on here, this value won't actually be the right value. But what I can do is say, well, if my calculated value, VC, which is the calculation of that, and I've got the VO, which is the observed value, take difference, that's going to give me a V diff. That tells me exactly how far out that pixel is. Now the reason it's out is actually going to be related to not its value, but obviously all the ones around it. But if we pretend that that one is the one that's caused the problem, or that one has caused the problem in proportion to all the other, I can give this assign this a new value. So correct it for the missing percentage or whatever. So you, pixel, are responsible for this much of it being wrong, and then see what that looks like. And I could iterate that, just keep going round and round and round. So we can watch that. Again, it looks promising, but very quickly we have to, it saturates out because there's only a certain maximum and minimum brightness, and I think if anything it just creates art rather than solving the problem. So to be able to try to get more information out of the picture than we get from just the average doesn't look like it's possible. Not unless, if you were maybe an astronomer and you were pointing your sensor like this at, say, I don't know, a galaxy. Here's a galaxy. Here's a galaxy, like that, very big. And I'm going to put my gigantic sensor over this galaxy, like that. And it's going to chug across here. Same problem. I can't get the value of the galaxy out because I don't know the value of here. But as an astronomer, perhaps I might be able to point a radio telescope or something here and say, I know for certain, I know 100% for certain that this area is dark. There's absolutely genuinely nothing there. Now, armed with that information, as this sensor starts to arrive collecting data from this galaxy, I know 100% that my sensor was collecting 0 here, and as it starts to touch here, the value, my reading, my average value will start increasing. And this is the unknown that can become a known and then can enable me to actually figure out what's in the picture. So I think there are ways of getting more sensitivity out of the thing than it can offer because of these unknowns. But for me, with a light sensor stuck on the end of a camera, I don't think I'm going to be able to compute them. Okay, a few final thoughts on this sort of project and the things that you might need to think about if you're going to attempt them. Number one, my analog to digital converter has a conversion rate of 800 samples a second, which sounds a lot, sounds perfectly adequate, but the screen resolution that I'm using is 800 pixels. So in order to scan across one line of the screen, that's 1 second, isn't it? 800 a second. But it's worse than that because the A to D I'm using is multiplex, so it can only actually make one measurement of X, Y or light on the joystick in that time. So actually to scan across the whole screen, it's going to take 3 seconds for one line. Becoming quite a significant amount of time to scan an interesting part of the screen. And that's definitely a limitation of this device, that the A to D isn't fast enough. Certainly if we're going to build an image that looks like something, you're going to need something a lot faster than that. So could consider getting a faster A to D than the one I was using. Another limitation of this, having a multiplexed A to D, is that it takes a reading of X, Y, light, X, Y, light. So the data as it comes in is actually, I actually had it X light, Y, X light, Y, X light, Y. What that means is that the X, Y and light readings don't line up. Now it can compensate for that mathematically quite easily because you can work out the velocity from the last X and this X, and this, I actually put this into the code for this one. You can work out the difference between the last X and the next X, and then you can work out where X would have been at the point that Y, the light, was measured. But again, something to think about with a faster A to D. If it wasn't multiplexed or if there was a delay in the readings, then this is something to think about in terms of improving the accuracy. Another thought about this is so it's the speed of the A to D is quite slow. The exposure, I really kind of worked out how to get the best exposure out of the device. I didn't do anything in the beginning to measure the linearity of the device in terms of, it's a phototransistor, and I don't know whether it's pretty much either on or off. Whether I should have gone with a cadmium sulfide cell or something that maybe has a bit more of a linear response. It might have made it look a bit more interesting. And also how do you interpret the values? I think a linear response to light may not be the best thing. I think maybe cameras actually have more of a kind of logarithmic response. I don't know. So because I never really kind of created an actual useful picture, I never really got into the kind of response or how do you measure the exposure in the first place. And because it's so slow, if the sun moves, the whole picture is going to be ruined anyway. I think another thing that might be useful in the future would be to use the servo motors. So that would enable the project to, I could leave it for an hour and a half scanning, come back to see what it's done, and then can make some more decisions about how to improve the image quality after that. But that's going to involve more expense and more thought and more time. Another thing I thought about was the actual joystick itself. In one plane, because the joystick moves in two planes, it has some kind of, it's hard to describe. So if that's turning one potentiometer, there's a thing that turns the other potentiometer, but mechanically there's probably a bit of wobble in that. So as you change from up to down, then there's a delay before it moves. So again, this might be adding some kind of noise. So I think it might be changing the depending on the direction that you're moving the joystick around. If you're moving up and down or round and round, it might actually change the characteristics of the X or Y measurement. So that's something to think about. Other than that, I think this project has it's sort of delivered what I was after. It's created some images that sort of show light and dark, and it's got me thinking about weighted averages and what you lose in terms of averages and stuff. So that's the end of the Sensing Joy. That is the end of the Sensing Joy project, and I hope you really enjoyed it. It's been a real journey for me. If you've got any questions, or you think you want to have a go at this yourself, or want to attempt it, contact me, drop me a comment below or whatever. I'm really happy to share my experiences with this one. Thank you ever so much for watching. Thank you for your support of the Inner Loop, and I'll see you on the next video, which there's some new Raspberry Pi stuff. I'll say no more for now. See you next time.